Then we're gonna be defining what rate limiting is as well, just because. Whoa, I have I don't know what that is. All right, it went away. Doesn't matter. All right. Uh, the technical difficulties. I'm sure there's gonna be more. So enjoy. Okay, but yeah, where was I? Oh yeah, the contents. So yeah, we're gonna define what rate limiting is as well, just so that everybody's familiar before we kind of dive in too deep. And we're gonna be looking at this initial implementation and how we improved attentive performance, and then some sort of extra stuff at the end as well that I thought was interesting to share. So yeah, so the talk is gonna be about this finer grained rate limiting that you can configure, you or your team could configure for your endpoints in your services. And this is not the type of rate limiting that's gonna replace something like CloudFront or something. And and we also, of course, our infra team has done their jobs, and we have like actual real defenses for them, like denial of service attacks. But sometimes like a smaller attack can also be as destructive as a larger one if you haven't prepared properly. So there's always a need for these like different types of different levels of rate limiting. And let's get into the definition. So it's a technique of controlling the amount of network traffic that a system allows over a specific period of time, and it's so that you can kind of make sure that your services are stable and nobody's kind of cheating. And yeah, there's also like a nice little picture that I drew about the rate limiting out down there. Maybe you can see that. Hopefully it's not too low. So you can see clients making them some requests, and then the rate limiting lets only some of them get passed, and the bottom three are rejected because there's too many requests already. And yeah, so okay, maybe you're still thinking, why do we actually need this sort of solution like at this level instead of just depending on some cloud provider? So some endpoints might respond always reliably in milliseconds, but others, they can be slower. It can take a long time, and maybe there's something your services can't scale that much because of some dependencies. So you really cannot like have that many requests. You have like a limit, so you have to have limiting. And the these like larger edge solutions that are used for denial of service attacks and stuff, they're not as configurable for these tinier endpoints and not as fine grained as what we're going to be talking about. And yeah, then also just on the algorithm that we are like, there's a like just like with a lot of like computer science problems, there's a ton of different algorithms that you can use for things like rate limiting. And we currently use like a leaky bucket, or like close to it. Actually, it's not like a real leaky bucket anymore because of some of the things we've done that we'll discuss later. And actually, let's look at leaky bucket just as an example of a rate limiting algorithm. So leaky bucket. There's another one of my famous drawings. You know, you can see there's some leakage going on in the bucket, and yeah, it's based on like, maybe by the name you can tell it's based on this like analogy of a bucket that's leaking, and it's leaking at a constant rate. You know, and if you have if the actual amount of water that comes into the bucket exceeds the constant rate that the bucket leaks, the bucket is gonna fill up and it's gonna overflow, and it's going to then miss some of those drops of water. They're gonna be rejected. And this also means that, I mean, in terms of like actually rate limiting, this means that you will limit traffic that sort of exceeds the rate that you have set as the proper rate, and like it'll over time it'll like reach that tipping point. And but it also means that if at any one given point of time you at once you receive too much traffic, it'll also like start overflowing right away. And yeah, in practice though, you don't you're not supposed to like stop the traffic sort of, or like you don't want to dictate that it's actually going at a certain rate, but you want to like keep track of the what would the imaginary bucket, how many drops of water would you have in there, and then detect that okay, now we're actually going overboard. And yeah, I think we can kind of move on to the next slide. So the initial implementation that what no laughing in the audience, all right. And the so we were working on this Go service at Wolt a couple years ago, and we didn't have sort of a standardized way of like doing rate limiting in Go yet. So we just wrote a simple custom solution for this rate limiting, and yeah, seemed to work fine, right? And this solution was nice. It allowed us to make these educated decisions for each endpoint that I was talking about earlier. And it also like it shared the state of the rate limiter between all of the different like instances of the service with the Redis, which then this was like really important for us because it allowed us to like set accurate rate limits that are shared between the instances. So if you can maybe you can imagine if you set a rate limit and the rate limiting is not shared, then you might run the risk of like having one instance reach the rate limiter but the other one still hasn't reached it, and if your load balancer like moves the traffic around, like you might like randomly get past the rate limiter or not. And also like depending on the amount of instances that you have, like the rate limit actually changes, like the total rate limit. So yeah, that's why we want the Redis. And yeah, the negatives that it had was that yeah, it was sort of unnecessary to reinvent some of this stuff, and so kind of cost of maintenance came to us. And yeah, turns out the performance was actually not that good, or not good enough when we actually got some attacks. And yeah, this initial implementation sort of, well, it got attacked as I mentioned. This was somebody like clearly with malicious intent, and so it wasn't some like enthusiastic bot scraping our site. So we actually got like around 100 times the request per second that we would normally get, and that was too much. The service itself sort of kind of was able to take the traffic, but the rate limiting, which we're talking about today, that was the bottleneck. The root of the problem was that for every single request that was coming into the service, we were actually making two requests to Redis. We were checking the status of the rate limiter, and then we were updating it after that when we were if we wanted to like increase the count of the key. So this sort of you can maybe imagine if we're getting 100 requests, let's say, that means we're making 200 requests to Redis just to kind of like rate limit everything, and then we have to also like do everything after that. We're like at yeah, a lot of requests, and this became the bottleneck. There were too many connections open simultaneously, and like even if like legitimate traffic got past the rate limiter, it then like basically timed out because the service wasn't able to like do anything afterwards. If it had like if the endpoint had any like external dependencies, it just couldn't make requests to those anymore. And yeah, we started timing out. But with this sort of we were then able to get improving. So we had identified a clear bottleneck, and because of our bad or maybe good luck, the attacker was sort of pleased with their results, and they kept coming back again and a couple times. And this gave us an opportunity to iterate and improve our solution. And the first thing that we did, we got rid of the custom code, and we started using this Redis rate library. And yeah, it's kind of a nice little library. This sort of already like halved our calls to Redis, because with this Redis rate, we're able to make a single request to Redis. It runs some Lua code, figures out the rate limiting for us, and then returns the result. So that's cool. That's what we were looking for. Gonna get those Redis calls down. And but the sort of downside to this is that then, well, we are running the Lua code in the Redis instance, and this means that our like Redis CPU utilization went up a lot. And well, the next attack that we got, similar like, actually, well, it was more. We survived the next attack, but just barely, I guess. Like if the attacker was able to like do some more, like maybe the CPU would have been reached its limit. So it worked, but we already knew where the next bottleneck would be, so we got to thinking. And yeah, this might seem obvious, maybe, but to us, it really wasn't at the time. It took us some thinking, and I still remember the meeting that we were in where somebody suggested this. So, what do you do when you're like doing the same thing over and over, and you in a certain time frame, and you get the same result back every time? Well, you cache the result, of course, and that's what we did. And we picked Ristretto as our like in-memory cache library. Uh, there's a ton of these like similar ones that are all like competing for the same performance crown. So I'm sure somebody has their own favorite one, but this one worked well, so we picked it. And yeah, this got rid of all of those Redis CPU utilization problems that we had, and yeah, increased our performance by quite a lot. And you'll see that in the coming graphs. But a little bit more about Ristretto. It was helpful for us because Ristretto also supports like TTL keys, time to live keys. So when we got the results from the Redis rate library, we were able to then. It also contained like how long does it take for the leaky bucket to empty entirely. So what we did is we took that time, gave that as the time to live for the key, and cached the results, which we would then like check, obviously, like as the first thing in the rate limiter. So that's why we're not like it's not the pure leaky bucket algorithm anymore. We're sort of a more aggressive leaky bucket at this point. So if you filled up the bucket, you're already like, then you're rate limited until the whole bucket empties, basically. And yeah, and yeah, we got to keep with this solution, like this combination, we got to keep the Redis instance that shares the state between all the services. So yeah, still kept the same source of truth. And here, this is just like sort of there's a couple graphs right there. On the one on the left is just like a morning, a normal day, right? And some traffic flowing in. The green bars are 200, okay, that's good. And the orange stuff on the bottom, that's those are 429s. So somebody kind of exceeded their rate limit, but that's fine. It's just a little bit. And then on the right, you'll see some latencies. So there's like the P95 on top, and then going down the other ones. And yeah, looking good. But next, I'll show the next day, and keep the green part in mind, and just remember that it's still there. But yeah, you can't see it actually anymore, or maybe maybe you can see a couple pixels, but yeah, you could probably tell that the orange thing changes shape quite a bit. So that's the attack basically. And the more interesting thing, I think, is sort of the this one over here. What's going on over here? Are we like missing data entirely or something? But no, that's actually our latencies, our sub-millisecond latencies at this point with the new implementation. So we're really pretty quick at kicking out that junk traffic. And yeah, I don't think anyone like noticed this instance or this attack. Like I think I like noticed it on the next day when I was just looking at some graphs, because yeah, nobody it didn't bother us basically. No. Yeah, we were yeah, pretty pleased with this solution at this point. And here's the same like incident day, the utilization from Redis, like, yeah, I don't know, it went up a little bit, but still like less than 10%. So yeah, we can still run a lot of Lua and Redis if we want. And yeah, this slide maybe it's just while we were developing this, we were running the same load test against the implementation like repeatedly. So just some more numbers for you. You know, we like the original solution where we had like our P95 was 40 milliseconds in this like load test, which wasn't even like too crazy or anything. And I think it's just like a couple IPs or maybe even like a single IP load test, which is sort of like a very synthetic load test. Oh yeah, we went to like I don't know, is it like microseconds? I don't know. I think less than a millisecond. So that's good. Basically, just like a test of Ristretto at this point when we're running this load test. And yeah, the Redis engine CPU utilization, you can tell it went up with when we just changed to the Redis rate, but then it's like barely doing anything at the end. Yeah. So this all this work put us into like a really good position because now we were no longer like fighting against the performance. We actually like we were able to do like what kind of now we were able to like focus on actually helping other teams with like some more interesting like rate limiting features. And yeah, that's sort of what we focused on next because performance was not the problem at this point. So what other type of stuff did we then end up working on with this? So this slide sort of these are just some example like configuration names that we have, but yeah, no fancy visuals for this one, but uh, so yeah, we for like if you have like a logged in user, you don't have to do anything too fancy. Like you can detect them with the token, and if it's not a valid token, you kick them out instantly. If it's a valid token, it's somebody who's logged in. It's a actual customer for us, and yeah, we can just do like simple rate limiting based on the user. But when we are talking about anonymous traffic, that's sort of where it gets more complicated, and that's all of the actually like problematic traffic is always basically anonymous traffic. So the basic anonymous rate limit that we had originally, it's cool and all. It's the IP based one, like the sort of the one you maybe is like the first one everybody always thinks like let's use IP, of course. But that also that can be kind of cool, but you really when you have like a service that maybe can't take that much traffic, you can't just rely on an IP because even if you set like one request per minute for each IP, somebody can just get like a million IPs and make them all do a request at the same time. And so yeah, you can't rely on that for much. But what do you do then when you have to kind of like let go of the IP when you're rate limiting? Well, one thing you could do is sort of look at this anonymous total rate limit. Like what about that? Uh, what if I just give everybody the same? Everybody's in the same rate limit, like all the anonymous traffic. Uh, well, then you sort of run into the issue of all right, what do you even set the rate limit as? Like you have to go like low enough to not cause any issues for your service, but then you kind of also have to be high enough so that some like bad actor can't just take your like whole endpoint offline like with their laptop or something. So it can be if you know that you have like some specific limit, that can be like good, but maybe not what you sort of always want to use. But then okay, what do you do then? Well, that's sort of that's where the magic is sort of, and I'm gonna like sort of leave it as a secret sort of as well. But you're gonna wanna look at your data or the metadata of your traffic. It's gonna depend for everybody also. So if you look at your traffic that's coming in, and if you see patterns, if you see sort of groups that you can kind of detect and rate limit, then that sort of where you might want to focus on. You want to look for groups that are larger than just a single IP1, but are also smaller than like literally every like request. So somewhere in between. When you find these sort of groups, you can create rate limits for them, and yeah, then you can get rid of like huge chunks of traffic, and or pretty easily. And then also just as the bottom on the bot rate limit as a reminder, sort of remember to also think of your like SEO. Like there's a lot of like bots that don't actually, they're not like harmful to you. They're actually good for your platform that you get visibility on something like Google. But so maybe you want to consider actually if you have some endpoint that Google wants to make a request to, but also somebody you don't want to like somebody's making too many requests as well. You might want to have something like a bot rate limit and then detect the actual good bots. But yeah, just be careful with that and do your homework and how to actually detect them properly, because there's a lot of people who also want to just put Google bot in the request, and if you believe them, then they're gonna get some extra requests. Actually, okay, I think yeah, let's talk about it here. So yeah, with this like with all these different sort of like rate limiting settings that we came up with and the increased performance, what we ended up doing is that we actually allow teams to have like multiple rate limits now at this point for their endpoints. And what this means, well, so this means that you can have like the anonymous rate limit and the bot rate limit at the same time, and the rate limiter will actually go through the correct rate limits for you in the correct order, and check all of them in a sequence. And this has not yet been like, this has been working very well because it's sort of like a limited use case usually. Like teams have a couple of them, but as we sort of grow, it's maybe like could be the next bottleneck. Like if we have like too many rate limits in some endpoint, it could be sort of like a thing to look into. And actually, yeah, so in this sort of like potential future slide, I was like thinking that, yeah, maybe we want to actually do something like modify Redis rate in the future, or write our own like solution for that part. If we want to like if we want to like tackle that thing again, see how if we can do it better this time. But what would be cool is sort of like having Redis rate, but then since we have a bunch of different rate limits and more incoming most likely that we're looking into, if we could run like more than one in that same Lua script and then get the responses for all of those at the same time. And yeah, there's just other ideas, like maybe we can actually also have like multiple like time windows for the same rate limits, and yeah, that could also like sort of fall into the same category. Yep. And I think that's my last slide. I think I'm in the that's it slide at this point. So
Okay. Can I hand over?
Yep.
Before we go to the Q&A session, I have short heads up. Today, each speaker will choose the question he likes the most, and that person will receive a swag bag from Wolt. So please ask questions. We also have some people on the second floor and separate dedicated person with the microphone. So please asking question. Anyone should go first? Okay, this one.
Thank you for the presentation. I have a question regarding the attack and the slide with latency. It was a bit confusing for me. Maybe next one with numbers.
Oh, this one?
And maybe next one as well. Yes. So it's dropped from 40 milliseconds to 80 microseconds. But
yeah,
if I remember correctly, the lower latency is better for
yes.
the performance. is it just a typo?
Oh, did I?
Yeah, it seems like the performance increased during the attack.
Oh, no. This slide was about the like when we were developing the when we were developing the solution. I was running these load tests, and this is sort of like the load test results are here. So the load test with the original solution, it gave us a P95 of 40 milliseconds. But then once we had sort of gotten to a modern version of the implementation, that we were actually at 80 microseconds with that same load test with the same
Ah,
load sort of. Yeah.
okay,
So the
got it.
performance went like way up basically.
Okay, thank you.
And here you can see sort of like similar results. Like these are just like normal P95s for these endpoints, and here like well all of the latencies are like sub millisecond here, just because of like the crazy amount of the rate limited traffic here. Like here, there's still like the normal traffic going on over here. Like this traffic is all still going on over here. So you can just sort of the scale of the difference between like what's happening. That sort of causes the chasm here. Yeah.
Okay, got it. Thank you.
Do we have someone from second floor? Okay.
Yes, thank you for the presentation. Just wanted to ask, how do you actually integrate? Like, what is your service? Is this HTTP service? How do you integrate it with your API gateway, for example, and make it easy for your customers to configure things as well? Do they go through your team, or they can do it somewhere in YAML? Or what is your API gateway kind of where this one is called?
So we have this. We have a Go service. We use Gin, and this is one of the middlewares in our Gin service. And then, so it's like for every endpoint we run this middleware basically. And then we have a YAML file where you can go in and like configure your endpoint and put in all the rate limits you want, and that's how you get the rate limiting. Yeah.
Hi, thanks. By introducing this caching, local caching, let's say, you kind of replicate the state required by the rate limiting.
Yep.
Did you notice any memory consequences of doing so? I mean, if the attacker kind of figures out what's the rate limiting key, he might have used that.
Yeah. I mean, the memory footprint of the service didn't really change too much. It's very low on the memory usage, so it's not. And so we definitely could, if it was, we could totally just bump the memory up. It's a so far non-issue, and yeah.
We have a question here.
Right here. Yeah, thank you for your presentation. Yeah, that's cool that you implemented these things. My question about how do you, currently you use these things, and how do you set up these? Because on my experience, every time we have just implemented new service, we don't know which RPS we have, and we have to adjust our rate limiters. And how do you do it in your cases? Because you don't know, in the nighttime that's one RPS, in the daytime that's another, and how do you do?
Yeah, that's sort of I think it's sort of a constant thing that you always work on. You can't, you'll never find the right one. Also because at least this service sort of has also, at the same time as we've like kept developing it, it has grown. Like this service has started receiving more and more traffic. So if I set a rate limit like 6 months ago, it might be that maybe it can do more now, or maybe the users are actually like calling it more, and so you have to sort of keep an eye on it. But usually how it actually goes in like real life, it's that okay, some like dependency of the service is now receiving like too much traffic. So okay, we have this service is then basically taking in like too much So let's go in and adjust this. And I work with the teams usually. They'll ping me or like my team, and then we'll basically go into Datadog and like analyze the situation and then make a decision and keep an eye on it. Maybe like for the next week, and then that's how we kind of come up with the rate limits. But they'll change. They're always changing. So yeah.
First question, like how many replicas at max on a server? And next question, why you need this shared state? Because with proper load balancing strategy, it is not needed.
Oh, it's not needed. Well, that's I guess I either don't know or have to disagree because for us that's sort of been a requirement so far that we don't have like a predictable for all of this traffic. We don't have a predictable load balancer for this. It could technically change, so we do want to make sure that we keep track of the state. And what was your first question? Oh, okay. Yeah. Yeah, there can be a lot of writes and reads, but the local caching sort of cuts down on that as well, like a lot, because then once you have sort of one of these larger attacks, you only have to kind of move it so many times, and then after, just if you're like, let's say your service gets 1,000 extra requests, but on the first one you already figure out that okay, this is rate limited, so I'm gonna locally cache it now. So then on the other 1,000, you do not have to go to the Redis, and then once you sort of multiply that by the amount of instances, you only get like a handful of more of them, depending on the count of the instances. But of the rate limiter, yes. So yeah, if that was sort of unclear, once the rate limiter in the Redis returns that okay, this is your last request, that instance that receives that instance lets the traffic go through, but caches okay, no more requests, and then the other instances of the service, they will receive, if they get traffic from this for this key, then they will know that okay, there's 0 left for this, so they will also cache it for whatever time is still left, and then not let that traffic go through anymore, like at all basically. So yeah, and that's how the state gets shared through all the instances. There's only like a single request needed by every instance to get the state, and then they'll remember it.
You have another question here?
Yes.
Hey, thank you. I'm here at the balcony. Thank you for the speech. Question about the optimizations you did. You mentioned that you use the Redis rate, right, for the
Yes.
rate limiting and this ristretto.
Yep.
As I know, Redis also has a kind of solution for caching because it's like caching library. Why don't you use like Redis for the both optimizations and pick the ristretto?
Oh, like instead of ristretto, use Redis.
Yeah, Redis itself, because you would have like one, I don't know, database with all the caching and the rate limiting at the same time.
So we want to get this performance, we had to get rid of those requests to Redis. That was the bottleneck. So if we couldn't just like once we were at this point, okay, I mean it did work, but we did not get anywhere near close to the performance. Like Redis wasn't fast enough basically for us. It is super fast, like, and almost for everything it's like fast enough, but for the 100x increase in RPS that suddenly happens, like we haven't been able to think of anything that was like sort of gives us like the instantaneous performance that we need for that. So that's why we had to locally then cache the result. Because this is like, yeah, the Redis rate with this, the Redis already does contain all of the information.
All right. Yes. So you mentioned that you could use metadata to group, I guess, requests and then have different rate limits for these groups based on that metadata. Is there any risk that someone would figure out that this is something that is being done to rate limit and then basically mimic the metadata of like a good actor, I suppose?
I guess technically yes, and that's why like I didn't go into details on like what kind of grouping we're doing, so that sort of everybody can kind of look into that themselves. But yeah, we're keeping that as a secret, and yeah, because yeah, technically if you knew everything that we're doing, you could optimize your attack. But
Right, so you're saying that there is like enough to this analysis that it wouldn't work on like a generic level. They would have to have like a lot of knowledge on how this grouping is being done using the metadata.
no, I'm just saying that if you knew exactly how our system worked, then you could, with the same amount of money, you could do a better attack. That's all I'm saying, I guess.
All right, thank you.
Yeah.
Yeah. Thanks for your presentation. And I would like to ask, what are the best practices for setting rate limits, like per endpoint or per user or globally? What are the cases you feel?
Let's see. I guess you sort of, well, you want to make sure that if we're talking about like a logged in user, you want to make sure that the app or website that they're using is actually like usable with the rate limit, and probably a little bit more than that as well. So that's sort of your lowest limit for a logged in user. Like you can't have it like start limiting a real user that's just browsing the app normally, because that's when you sort of like start losing maybe money or something. And then on the upper end of like how high could you put it, then that's more of a sort of a decision in terms of like what can the service take. Like if you divide them, if you have 5,000 users, how many requests maximum could they all make in a minute without your like service having issues? That sort of a thing is what you'll then think about. And then you'll probably pick something in like between that makes sense for you.
Yeah, thank you so much.
Hello. Yes, thanks for the presentation. So one question is like, how do you actually set up the whole Redis for this middleware? Because I believe this is like a middleware for all the microservices. So there must be like a many requests coming at the same time to read and write the Redis. How do the Redis is being organized? Do you have like a one single like a large Redis cluster only used for this purpose, or you have like a separate Redis for each service to handle the read limit?
Oh, it's a single one. It's the shared Redis. That's the whole like point of it, so that it contains the same information. Like you need it to be like if you had a Redis for each instance of the service, then we wouldn't need it. Like we only need it because we want them all to use the same one, so that they can share the rate limiting state.
But this Redis sounds like quite critical because all the requests actually will use this Redis.
That's
Do you have any
correct.
kind of way to handle this in case the Redis fails?
Oh, in case the Redis fails? Well, then, yeah, of course, your service has to have like fallback strategies. So maybe you have a circuit breaker. Maybe you decide that, okay, like if my like Redis is down, can I make an intelligent decision? Like I'll still have my local cache. It will still live for a while. Okay, I can look into that. Or maybe I want to like make a decision of like, okay, I only will allow authorized traffic. For example, you could make a decision like this to like keep your services like safer, even though you can't do the actual rate limiting itself anymore. So there's a lot of things you could still do, but definitely the Redis is critical, and that's why we have like invested time into this, and we are using the local caching to sort of protect it
All right,
as
thank you
well.
very much.